All right, guys. So here we're going to just go really quickly over some key points that I think you might find helpful as we're going through here. For the first couple questions, it's just straight up kinematics. At what height above the ground do the balls collide? Well, all you need to know is um, the initial speed of the bottom ball. We know that the acceleration due to gravity is 9.8 meters per second squared. And we can figure out that after 2 seconds, how high it is that they collide. Similarly, for the second ball, we can find out how far it falls in 2 seconds. And since those things are meeting in the middle, right, here's our cliff. Um, and I have, one ball at the top just dropped, one ball at the bottom. We're just going to go ahead and assume that somehow it was launched from the exact bottom of that cliff. At some point, 2 seconds later, we know that they collide here. That's enough to start with. All right, I'm just going to label this. This is at T1. So, um, what I wanted you to think about, though, as we get into these total momentum ideas, we can look at each of these things individually, find the final velocity of each one individually, calculate the momentum of each one individually, and then add those individual momentums together. It's doable, it's possible, but it is somewhat involved, and there's a lot of calculations that go in here. So, what I suggest we do is we think about how we define a system and we use that to our advantage. So, here I could say, well, what if I treated these two balls as a single system, right? In that case, I can find the initial momentum of this system is the sum of those two momentums. And a lot of the collision stuff that we've looked at before says that in a collision, the momentum is conserved, which is true. But if we say the momentum is conserved when there's no outside force. So in this case, for these balls, there is an outside force and it's acting on both of them. And so I can use impulse and momentum on this entire system just like I would for the individual objects. So when I think about trying to figure that out, right, we say, and again, I can't type all my symbols in here. Delta P, that's change in momentum, is equal to force times time. And so I can do that for the total here. And I can say, well, gravity acts at 9.8 meters per second squared, 9.8 newtons per kilogram. So find the force of gravity acting on the system, which has a combined mass of 7 kilograms. Find that force and multiply by time, and now I have found the final momentum of that system. And after that point, they are going to move together. And so that allows you to find the total momentum before and after, which are going to be different, a lot easier. And then, if we know the momentum of the combined balls and then they do combine, then I know that they're going to have that same total momentum, and I'm just going to divide by the total mass. So that makes these questions a good bit easier. Another really interesting thing that we do want to be able to kind of wrap our head around, we didn't really talk about it at length. We talk about center of mass, all right? And so, as you might imagine, I have a 4 kilogram ball at the bottom, a 3 kilogram ball at the top. the center of mass is probably going to be somewhere around, the center of mass is going to be somewhere at the start, um, closer to the 4 kilogram mass. And the other interesting thing about that center of mass is because it's the center of mass of that system, and we have a constant force, the force of gravity acting on there. If we followed the path of the center of mass, the center of mass would follow the same path as an object in free fall, right? Because for this system, that system is falling down at a rate of 9.8 meters per second squared. The center of mass starts, if you can imagine, right, with an initial upward trajectory, but it's going to follow a normal parabolic path to the ground, because now I'm looking at it as an entire system. And so sometimes things can be complicated for individual objects. Like if we actually think about what's going to happen here, these balls are going to collide. And actually, at the point that they collide, if you think about it real quick, you have 2 seconds, right? So round it off to 10 meters per second squared. After 2 seconds, each of them is actually going to be traveling at 20 meters per second in opposite directions, but the upward moving object has more mass. And so that means that when they collide, it's actually going to, the combined mass is actually going to go up a little bit and then come down. But the center of mass of this whole system is going to follow just normal parabolic trajectory because I can reduce these things down. So you are greatly benefited by using the conservation of momentum for the entire system, or momentum and impulse for the entire system, instead of doing each one individually, which I expect would be your initial approach. And we've kind of done all of that with momentum. We can do the same thing with energy as well, except in the end, we do know that during that collision, there is some energy lost. But once that energy is lost, and we know that final velocity, we don't necessarily have to solve for the whole motion to the ground to know what our final velocity is going to be. We can just use conservation of energy, like we would before, and solve it that way. So this is just kind of a good overview of what I wanted you guys to look at and think about. Hopefully you'll find it helpful, and I will see you guys tomorrow.